Hello, students. We're continuing on with our third and fourth lesson, which is lessons 1.3 and 1.4. And again, this is for Algebra AB right now. Okay, let me go ahead and share the screen, and let's take a look at lesson 1.3. Now, lesson 1.3 is on page 19, and this is what you should be seeing if you have your book open to page 19. Real numbers and the number line. Okay, objectives: to classify, graph, and compare real numbers and to find and estimate square roots. Okay, you can take a look at this pattern here. There's one block. Now, if we double it in both directions, meaning double it to the right and double it going up, then we now have 4 blocks. Now, if we go 3 blocks on the side and 3 blocks up, we now have 9 blocks. If we go 4 over and 4 up, we now have 16. Okay, so that brings us the first 4 square numbers: 1, 4, 9, and 16. Now you notice I'm counting the blocks, I'm not counting the numbers at the bottom. The numbers at the bottom could represent maybe like just the length of one side. This is 1 unit long, this is 2 units long, this is 3 units long, and this is 4 units long. But when I go units up, the same number that I go long, then I end up with bigger squares each time. In order to count the squares, then I must have those specific numbers, okay? Meaning that these numbers are what we call square numbers because they represent a number times itself. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and if it had it, 5 times 5 would be 25, and there'd be 25 little orange blocks there, okay? Now, let's go over some vocabulary. In algebra, a number is a square root of a number b if a squared is equal to b, okay? For example, 7 squared, or 7 times itself, is equal to 49. So, therefore, 7 is the square root of 49, okay? Now, we'll go into a little more detail on that later. But you can use the definition above to find the exact square roots of some non-negative numbers, and you can approximate the square roots of other non-negative numbers. The radical symbol, which looks something like this, indicates a non-negative square root that is also called a principal square root. The expression of the radical symbol is called the radicand. Okay, if you take a look here at the bottom, you can see the radicand is the number that's in the square root symbol, and the radical symbol itself is showing that this is a radical expression. Together, the symbol in the radicand form was called the radical. You'll learn more about negative square roots in lesson 1.6. Okay, but if I were to continue, I could kind of give you some more examples here. Okay, simplifying square root expressions. What is the simplified form of each expression? Okay, a radical 81 is equal to 9. Why? Because 9 squared, or 9 times 9, is equal to 81. So we can say that 9 is the square root of 81. So again, the idea here is that a number times itself equals another number. Okay, now that's pretty well known. 1 times 1 equals 1, 2 times 2 equals 4, and so on. Okay, but as you know, exponents is sort of like a fancy form of multiplication. Well, radicals is sort of like a fancy form of addition, and kind of like the same, division. I said addition, I don't know why I keep saying addition. It's a fancy form of division, and it's very similar. Now let's take a look at the fractional one here. You may have learned this at some other point, but I have radical 9/16. Now, since 9 is equal to 3 times 3, and 16 is equal to 4 times 4, then When I take it out of the radical symbol, the 9 converts to its square root of 3, and the 16 converts to its square root of 4. So radical 9/16 is equal to unradical 3/4, just like radical 81 is equal to unradical 9. Okay? You can figure it out by redoing the work. 3/4 squared is equal to 9/16. So 3/4 is the square root of 9/16. Now, if you choose to do the got it ones on your own, you're more than welcome to. They're right here, and they're also in your book on page 20. But I'm going to jump to the rest of the lesson. And if you could please take a look at this paper here. Okay. Lesson 1-3, real numbers and the number line. Okay. Now, there's 5 basic categories of what we call real numbers. Real as opposed to a theoretical number that somebody imagines, or numbers that basically just don't exist. Okay? First, there's what we call natural numbers. Now, natural numbers are basically numbers that start with the number 1, like 1, 2, 3, and so on, and they count up. Now, the idea of natural numbers is, I always think of like a very young child, like a kindergarten kid. When they count things, they basically start at 1. You don't really start lower than 1 because it's not really natural. You know, if you're counting apples, you don't think, oh, well, there's no apples on my table. Then you start crying. How come I have no apples and the other kids do? Okay, so the idea of natural numbers is you don't start counting until there's something to count. I mean, that's a very natural way of thinking. Okay. B, whole numbers starts at 0 and counting up. So like 0, 1, 2, 3, 4, and so on. Okay. It looks like conks, but that's actually counts. Sorry about that. Now, designating them whole numbers, other than the inclusion of 0 in the number system, the idea of a whole number is that it's not any one number that's cut into parts. Okay. Obviously, numbers are made out of parts. Like, for example, 2 is made out of 1 and 1 again. Okay. 3 could be made out of 2 and 1 added together. I don't mean that type of cut apart, but I mean literally where we cut lower than the number 1 but larger than the number 0. Okay? So that brings us to part C, which is integers. Now with integers, you can see my number line is started at -3, -2, -1, and then I go to 0, 1, 2, and 3. Basically, integers count up or down from the number 0. It counts up or down. Now, the idea is integers could be a system of all whole numbers, meaning that they're complete numbers, and their opposites, okay? 1 and -1. 2 and -2, 3 and -3. And if I continued on, 4 and -4, the idea is every number has an opposite. The opposite is usually represented by a minus symbol in front of it. And of course, the opposite is true. If I say a negative number, its opposite would be a positive number. Okay? It would not have a negative sign in front of it. Part D is rational numbers. And I start it with -1/2, 0, 1/2, 1, 1.5, 2, 2.5, 3, and so on. Now, rational numbers is sort of an algebraic code name for any number that contains a fraction or decimal, sometimes a percent. Since percents do count parts of one whole thing, then they are also compatible with fractions and decimals, but sometimes they can represent whole numbers too. So percents work very much the same way as fractions and decimals, but we'll go into that in a different lesson. Okay. Bottom line is rational numbers basically means any system of numbers that contains numbers that are not whole. Okay. When I say whole, I mean smaller than the number 1 and bigger than the number 0. Okay, so well, you might be like, but Mr. Bauer, you put -1/2. Is that an integer? Because integer is kind of a code word for negative numbers. No, -1/2 would not be an integer. Why? I'd like you to tell me, but since we're not in class together, I'll go ahead and tell you. -1/2 is not an integer. Yes, it is negative, but I want to remind you that the definition of an integer is any whole number that is either counting up from 0 or counting down from 0. Even though -1/2 is counting down from 0, -1/2 is not a whole number. Okay, so it would go into the category of rational numbers. Now, one thing I have to say for A, B, C, and D, meaning these different definitions and the examples here, I want to remind you that every succeeding definition includes the previous one. Okay, for example, rational numbers include fractions or decimals, but they also include all integers. So all integers are rational numbers, but all rational numbers are not necessarily integers. Let's move on down. Every whole number happens to be an integer, but not every integer happens to be a whole number, because a whole number also can only represents 0 going up, but an integer represents 0 going down as well. So all whole numbers are integers, but all integers are not necessarily whole numbers. Like, for example, -2, by this strict definition, would not be considered a whole number as it is written here as part B, okay, because it's negative. Now, whole numbers include all natural numbers. Now, this one's pretty easy. The idea is natural numbers do not include 0, but whole numbers do, okay? So if I say whole numbers, then I'm saying 0 counting up. If I say natural numbers, then I say 1 counting up. So every number from 1 and up is a whole number, but it is not necessarily a natural number. Or in other words, in the list for A, it doesn't necessarily include 0. Okay? Now, let's just go down to, let's see, I'll actually go like that. I didn't want to start the next lesson until I finished this one. But I wanted to talk a little bit more about radicals. So the next category, E, is irrational numbers. Now, with irrational numbers are kind of by definition. Well, okay, the book definition says an irrational number is a quotient of 2 integers. Okay. Now, again, you can probably put those words together. Okay, quotient means this, integer means that, and then come up with what that means. But for our sake, the quotient of 2 integers means this. It means a number can be written in the form of a fraction. Okay? Now, all fractions are division problems, so that would make them quotients. Okay? Because quotient is the answer in a division problem. But take, for example, the fraction 1/2. Okay? So you could call this a quotient because it is concurrently a fraction and a division problem at the same time. Okay? An irrational number, however, is a number that cannot be written as the quotient of 2 integers. Okay? Well, what do I mean by that? Typically speaking, an irrational number is written in the form of a decimal. A very famous irrational number is the number pi, which some of you may remember as 3.141598. And I don't remember all of the points after that. It would be impossible because pi represents a number that literally goes on forever. I guess there was a Google executive sometime in the past 18 months or so that had calculated pi to like the billionth like digit, how far it would go. Okay. Now, people in mathematics would probably be really excited about that. The average person is probably like, and like, who really cares? But the point is, an irrational number can be written as a decimal that doesn't repeat. So if you look here, it's not like 3.1414141414, it just keeps repeating, or 3.33333. No, it doesn't repeat, meaning that the numbers are different each time, and it doesn't cancel. Like, sometimes if you're dividing and you get to something, you end up with an answer like 3.5 or 3.75 or 3.375. And then eventually, as you're dividing, the number cancels and then you stop like continuing with the division. Okay? If you're doing it on a calculator, then sometimes the calculator will just give you a 2, 3, or 4 digit number. Now, calculators can be a little misleading because obviously a calculator cannot write all of the digits of pi because those digits will continue on forever. So sometimes calculators will just go to the end of the calculator screen and then they just sort of round up the last number, okay? And that can be misleading because it makes you think, okay, this decimal stops after like, 6 or 7 digits when the decimal goes on forever. So the idea is if you were to try to convert 3.141598 to a fraction, you couldn't do it because in order to convert it to a fraction, you have to put these digits over denominator that is representative of its place value, okay? Like for example, if I just had 3.14, its place value is the hundreds. So if I say 3 and 14 hundredths, then I could write it as 3 and 14 over 100 as a fraction. Now remember, we said a fraction is a quotient of two integers or a rational number, okay? But it can't do that because the number continues to go on. Well, so if I put out 2 more digits, all right, that's 10 thousandths. So I could be 3 and 1,415 over 10,000, but it still keeps going and still keeps going, okay? So the point is, since it keeps going, I can never come up with a denominator for it. If I can never come up with a denominator for it, then I cannot write it as the quotient of two integers, which basically means I cannot write it as a fraction. Now, some of you, if you were like in the class, would be raising your hand saying, but why don't you just like round it? Good, that's a good point. That's what most people do. If you want the fractional form of pi, usually people write it as 22 over 7, which is a rounded form, okay? But if you round it, it's not the exact number, okay? We just round irrational numbers because it's easier for our minds to consider that. Why do we have irrational numbers? I don't know exactly, but I suspect that it's related to the fact that our number system is what we call base 10. Basically meaning that every time you hit 10 or a power of 10, your number system increases, like the number of digits. Like we have 1 digit and then we get to 10 and now we have 2 digits. The next power of 10 is 3 digits and that's 100. And then 1,000, which is 4 digits. And then 10,000, which is 5 digits. So every time we annex another digit, it's always a power of 10. That's the point where our number system restarts, okay? Why is that important? Well, I've just noticed that some numbers don't gel very well with 10, so like 3s, for example, don't divide into 10 very well. So a lot of times on a calculator, if you divide something that's 3 or related to 3, you're going to end up with this repetitive number, like something 0.33333 or something 0.66666, that type of thing. And to the religious among you, sorry for using 666 as an example. It just pops up on the calculator a lot. Don't take that personally. Okay. Point going along. So irrational numbers, the most easy way to find an irrational number besides the well-known number pi is to find the radical of a number that is not a perfect square number. Take, for example, radical 2 would be 1.41 something, radical 3, radical 5, radical 6, radical 7. Okay? But you notice that radical 1 is equal to 1. Radical 4 is equal to 2. Hint, so radical 1 and radical 4 are rational. Why? Because when you reduce them out of their radical form into a regular form, then you end up with a rational number. Now let me clarify again what I mean by this, because we talked about this at the beginning of the lesson. So I said x times x here equals 7. So therefore, then x is equal to radical 7. Now if you remember, a radical means a square root, and a square root means what number times itself is the number inside of the radical. So for example, I may not necessarily know what x is, but I know that the first x and the second x in this problem, because they are the same problem, are equal to each other. Okay? So if x times x is equal to 7, then we could say that x is equal to radical 7, because radical 7 means whatever number times itself equals 7. Okay? Now, radical 7 is an irrational number. So unless your number is a perfect square numbers like 1, 4, 9, 16, 25, 36, 49, I'm just thinking of all the numbers times themselves. Okay, but moving on, if a number is, hold on just a second. If a number is not a perfect square, meaning that there is no whole number times itself, like 5 times 5 is equal to 25. So 25 would be a perfect square number. But 24, okay, what times itself equals to 24? Is it like 4 point something times 4 point something? Probably so. Maybe 3 point something times 3 point something. 4 times 4 is 16, and 5 times 5 is 25. So 4 point something times 4 point something would equal 24. Okay? So in a case like that, if a number like 24, if I cannot figure out what number times itself is equal to 24, then that would be a number that is not a square number. Okay, so this would be a good time for you to stop or pause anyways, and to work on lesson 1.3 homework. Thank you. Hello, glad to be back. I wanted to go over lesson 1.4. I know I spent a lot of time on lesson 1.3. I hope that's helpful to you. But anyways, I'm going to try to not spend as much time on 1.4, so let's go ahead and take a look at the notes there. Okay, lesson 1.4 is on the properties of real numbers. Now, let's go over the word property. Now, I know in English, property means like something that you own, like that pencil is my property or that phone is my property. We use the word property to mean real estate or land that people own as well. Okay, that's not what I'm talking about here. Property means anything that is always true about something. Okay, so a property of something is anything that is always true about something. For example, a property of the earth, and here's a nice little drawing of the earth, is that it is round or spherical. That is always going to be true. The earth is always going to be round or spherical. Now, if something came out of space and like blew a huge chunk out of the earth, and now the earth is shaped like a Pac-Man or something like that, then, well, for one, I don't think it would still be really the earth. I think it would just sort of crumble and destroy. That would be horrible. I don't even like to think of. You think the pandemic we're dealing with now is bad, think of that happening. But point being, if the Earth is always round or spherical, then we can count on that, and that would be considered a property because we know that to always be true. Okay? Now, let me ask you another question. Is the sky blue? Would that be considered a property? Yes or no? Is the sky always blue? Okay? Now, if you give the strict definition of the sky as basically just looking up at any given time, then the answer would be no. Because, like, if it's a cloudy day, the sky would be white. If it's like almost at dusk, then the sky could have a lot of orange and reddish kind of colors as the sun is sort of glowing into our atmosphere. At night, the sky is black or maybe a very, very dark brown, as some, astronomers have suggested. Okay? So the point is the color of the sky changes. Now, if I defined this a little bit closer and said, on a sunny day with the sun, full up in the sky, is the sky blue? Then yes, you could say that would be a property of the sky. The sky is always blue. Okay. And if you want to get super scientific, you could maybe theorize that because the sky has oxygen in it and oxygen shows up blue when light goes through it, that the sky is always blue as long as, a specific type of light is, unfiltered light is going through it. Or you could say, well, the sky is blue behind the white clouds that I'm looking at, kind of thing. Point being, I'm not trying to overdo it, but the idea is a property is something that we know to always be true. The Earth is always spherical, yes. The sky is always blue, no. Okay? But in certain circumstances, we can kind of depend on that. Well, properties also apply to numbers, meaning that sometimes with numbers and operations, and by the way, operations in mathematics literally just means addition, subtraction, multiplication, or division. Okay? And there's sort of some sub-operations like, exponents, which is basically just a fancy form of multiplication, as we discussed before. But the reality is it's just those four operations. That's what I mean when I say operation. All right, so let's take a look at the properties. A is the commutative property. And as I wrote it, if you move or switch your addends or factors, the answer is always the same. Addends means the numbers that are added together in an addition problem. Factors means the numbers that are multiplied together in a multiplication problem. Okay, let's take a look at B, the associative property. However you group your addends or factors does not change the answer. So if I group them by putting parentheses or brackets or something around numbers, let's say I have 3 or 4 numbers in a problem, then I can move those parentheses or brackets if it's all addition or all multiplication, and it won't change the answer. The identity property states this: if you add 0 or multiply by 1, you identify or rename or restate the number. And part D is multiplicative properties of 0 and -1. Basically, it means this is that any number times 0 is 0, or any number times negative is its opposite, or -1 is its opposite. Now I gave some examples for A, B, C, and D here. Let's look at the commutative property. 7 plus 4, if I switch them, then I have 4 plus 7. So therefore, they are equal to each other by the commutative property, even though they're switched. Let's see, 7 plus 4 is 11. 4 plus 7 is also 11. Let's try with multiplication. We said that 7 times 4 is equal to 4 times 7. 4 times 7 is equal to 28. 7 times 4 is also equal to 28. Okay? So if I move or switch my numbers or commute them, then that means that they are still the same. Let's take a look at B with the grouping. I have 3 plus parentheses 2 plus 2. Now we learned earlier that by order of operations, I want to do 2 plus 2 first, so I get 4. And 4 plus 3 is 7. Now let's try it once I move my association, or basically I move my parentheses. 3 plus 2 in parentheses plus 2. Now you notice I didn't move the numbers, I moved the parentheses. So let's do it by order of operations again. 3 plus 2 is 5. 5 plus 2 then is 7. I still get the same answer. Now let's try it with multiplication. 9 times 10 in parentheses times 2. 9 times 10 is 90. 90 times 2 is 180. Now I have 9 times parentheses 10 times 2. 10 times 2 is 20. 20 times 9 is 180. So see, I get the same answer even if I move my parentheses. Now, what's the purpose of doing this? Very simply put, sometimes you get problems that have numbers that are in an order that's not easy to add or not easy to multiply in your head. If you switch either by commuting or by reassociating, or which is basically just a fancy way of saying moving your parentheses, okay? If you move your parentheses or if you switch the order of your numbers to make them easier to add or to multiply, then you can save yourself time by doing a lot of the work in your head, okay? Now, one little note, it only works if it's all addition or if it's all multiplication. If you start moving parentheses around and some of it's multiplication, some of it's addition, or there's subtraction or division in it, it's not going to work. And when I say it's not going to work, there's always some situation, I'm sure, where you can come up with a number set that would work with one of the other ways. But I'm not talking about exceptions. The reason why we call them exceptions is because, well, with this number, it'll still give you the right answer, but it's wrong the way you did it. In a situation like that, it's just sort of an anomaly, something that happens because certain numbers work a special way that other numbers don't, okay? So, but in the general rule is if it doesn't follow that property, then it won't work, okay? There may be one or two occasions where it will work without the property, but those cases are exceptions. For it to be called a property, that means if you are following the property exactly, then it will always work, okay? And that would be the idea. All right, let's continue. Identity property of addition and multiplication. So let's identify 3 plus 0 is 3. You notice the answer, if I point to the arrow here, is the same as my first part of the question. 7 times 1 is equal to 7. My answer is the same as the first part of my question. Now let's take a look at D. 5 times 0 equals 0, and that would be the 0 property of multiplication. If you multiply it by 0, it eliminates the number and changes it to 0. If you multiply by -1, it gives you the opposite. So 6 times -1 is equal to -6. Okay? I'm hoping that that's very clear and enough information for you to start lesson 1-4 on your own. Please do your homework, and thank you very much.